As we get started here, I'm going to give a little bit of background about the type of data that we're collecting, and sort of a background about not just the study but the larger ecosystem in mobile health that we've been working on at SAGE and more broadly. I do want to highlight, if people are going to be participating in the hackathon and haven't yet registered on Synapse, please soon here go to www.synapse.org/dreamhackathon and pre-register. That's how you're going to get access to the data. We're going to be spinning up Amazon AMIs for people such that everybody's not downloading the data over the conference Wi-Fi all at the same time. It'll all be happening within AWS, so please go do that. So, mobile health, mHealth. I think when most of us think about mobile health, we think about this. We think about, a Fitbit or a mobile phone where we are tracking some sort of activity that we're doing. And that's great, but ultimately, I think we need to move beyond insular health tracking. So that's great for you to know about how many steps you are taking in a day, or how much you're sleeping, or the quality of your sleep. There's this great project that was funded by the Robert Wood Johnson Foundation called the Health Data Exploration Project, where they reached out to individuals and asked them a bunch of questions about their PhD, their personal health data that was being collected, in particular off of mobile phones. And when they were asked, who do you share your personal health data with, this was their response. So maybe not surprisingly, friends and spouses and partners ranked well above health professionals. Most of these apps, most of these services aren't built with sort of communicating with a physician in mind. It's for giving information back to the participant. But only a single participant, only a single user. And when these people were asked, would they be willing to share this personal health data with researchers, maybe not surprisingly, but over 75% said they either probably would or definitely would. And very, very few people, less than 2%, said they definitely would not or probably would not. But at the same time, when they were asked how important it is that your PhD be kept anonymous, the overwhelming majority, over 95%, said that they were at least somewhat, that was at least somewhat important to them. So we're sort of faced with this conundrum of how do we balance the desire of individuals to share their data with the importance of their privacy. And so as a little bit of background, I know most of you are familiar, at least to a certain degree, about Sage Bionetworks. These are a number of the different initiatives that we have. You can see the wisdom of the crowd as one of the spokes here, all focusing around open collaborative research. But one of them that I'm going to talk about today is citizen engagement. How do we go directly to participants and engage them, both in their health as well as in the research process? So about 3 years ago, we had the idea at Sage to develop a platform which we called Bridge. You can see here the individual data trackers. This is absolutely what a Fitbit monitor is at this point. You are getting information from a system. It is giving you your data back, and it's this tiny little loop. And what we were interested in is, how do we engage a study researcher, allow them to ask questions of participants, allow the participants to provide answers back, and then ultimately have the study researchers be providing results back to these participants and get an ongoing dialogue going. And so just about, I think, 2.5 years ago, we were awarded a grant from the Robert Wood Johnson Foundation to do just that. Importantly, in the early days of this, we saw this as not just a mobile application, but a suite of web-based tools to enable this. But in the early days of carrying out this project, we had the opportunity to work with Apple. And earlier this year, there was an announcement of Apple Research Kit. And there were 5 initial apps that came out as part of this initiative. This one down here is breast cancer, which is sponsored by Sage Bionetworks. This is Empower Parkinson's disease, which I'll talk about more later. This is data from this is what we're going to be using for the hackathon later. This is diabetes coming from MGH, a cardiology app from Stanford, and an asthma app from Mount Sinai. And there have since been 4 more research kit apps that have come out since then. And all 5 of these apps actually use the Bridge technology as their back end. They are each one of the apps is essentially communicating with Bridge, and then study researchers are consuming the data through Synapse, which many of you are familiar with in this room. And so I'm titling this Moving Beyond the App. You could call it Moving It Beyond the Sensor. Really, it's about building up a stack of services that are necessary to carry out research at scale through mobile technologies. So we have the concept of participant-centered consent, Bridge, which I'll touch on here in a minute, and again, Synapse at the tail end. So these are all sort of important pieces to develop this more broad ecosystem of collecting this type of data. I'm going to give just a quick overview here. What Bridge does is Bridge is a series of APIs that allows app developers to send data from the phone to a backend data service. And what Bridge does is it encodes that data. It separates out all of the user profile information, all of the consent information, essentially all of the personal health data that is identifiable into a separate store and provides a mapping that only the study PI has access to, and takes that ID, attaches it to the rest of what we call the study data, which is then bulk exported into Synapse actually nightly. So people who are conducting these studies are actually getting real-time feeds. Essentially every night they're getting updated data from participants that are participating in these studies. So the participant-centered toolkit. It's a concept of tiered information accessed by participants. So if any of you have participated in any sort of clinical research study, you have likely gone through some sort of consent process. It is usually a number of documents, a number of pages, with varying degrees of utility, as well as varying degrees of legalese sprinkled in within it. And part of what we're trying to do is to provide a mechanism by which we engage participants more and really try and put informed back into the informed consent process. Have it be less of sort of a checkbox, yes, we did this, and have it be more about trying to educate the participants. So we went with a pictorial dominant display, especially on the first information tier. So the first information tier, I'll show you an example here in a second. There's a text dominant second information tier, which sort of sits behind each one of these images, such that if the image and the short description up front don't really give you enough understanding of what's going on, there is more information sort of laying behind it. And then we actually ask participants a short assessment at the tail end to make sure that they understand sort of the core pieces of the consent process, which normally doesn't happen. It's usually just a signature at the end. So here's an example. We tell them that we're going to be collecting sensor data. The study will gather sensor data from your phone and personal devices with your permission. This is the learn more, so you can get more information about the types of data that we might be collecting. We tell them about protecting their data and how we're going to take appropriate measures to do whatever we can. But at the same time, we admit to them that there is a risk to privacy in this process. And we, again, tell them we're going to make every effort to protect the information, but we can't guarantee total anonymity. And this is really sort of behind what we believe with this consent process, which is that upfront radical honesty is much more important than placing radical restrictions on the data. So instead of really trying to lock down and ensure that nobody is going to have access to this data, and assuming that that means that it is that the privacy is quote unquote guaranteed, we're going to be very upfront about the types of processes that we're going to have in place, and also tell them that we can't totally guarantee that anonymity. So in the course of participating in these studies, participants are given the option to share their data with whoever the research institution is. In this case, it was Sage Bionetworks, and its partners and qualified researchers worldwide, or they can choose to share it only with Sage Bionetworks. And so this is really trying to put it in the participant's hand how much their individual data will be shared. So the data we're going to be working on later tonight is a subset from the ones who agreed to share it more broadly. And there were over 75,000 participants across those first 5 studies, and over 70% of them chose to share broadly. And I think that, is right in line with what that Robert Wood Johnson health data exploration study showed, which is that people really do want to make this data available to researchers, as long as they think that the researchers are doing responsible things with that data. So ultimately, again, how do we balance the security settings of a system or the system with the desires of those being studied? I mentioned Bridge. This is sort of the technical architecture behind it. Again, the important thing to know is that authentication and user account data are being stored completely separate from the coded study research data, which we'll be looking at today. We also believe that security as prevent access as much as possible isn't the answer. So again, locking down this data such that only Sage can see it, that only a small set of researchers can see it, really flies in the face of what most people want. I think Dream is a very good example of really trying to open up data, open up the research process to more and more people, get communities of people working on these data as opposed to having it be sort of siloed individuals carrying out the research. So ultimately, we're trying to give researchers the tools to do the right thing. We can't guarantee that they're going to do the right thing, but we can trust them. And again, a lot of you are familiar with Synapse, built on top of open RESTful APIs, programmatic clients. And in order to sort of build a research commons, which would enable secondary research off of this type of data, there are a number of things that we feel like were necessary to have in place. Importantly, access rights for controlled sharing. Just because an individual says they want to share the data more broadly doesn't mean that everybody in the world has the right to access it. So we're actually developing what we're calling a qualified user process, where individuals will have to provide a little bit more information about themselves and provide a research plan that we're going to share actually with the participants of these studies. So we're going to say, hey, Empower participants, come take a look at the researchers that are going to be using your data and the types of research that are going to be carrying out on that. As many of you probably know, we have the ability to track analyses with versioning and provenance within the system, and then ultimately, at the end of the day, a communication channel for publication or sharing of results for reproducibility. And so each one of the studies has a data access team. Only those individuals on the access team can access the data. They also have to agree to a series of terms of use, which many of you will see a little bit later. We will not be having to go through the whole qualified research process in order to get to the hackathon data. So we selected a subset of the data that was had minimal risk involved with releasing it, such that we can have as little friction tonight as possible. Here's an example of analyses tracked with versioning and provenance. So here is a patient subset of the tapping data that came from this study. The data is residing in Synapse. Here's a couple of scripts from Elias, who will be talking to you a little bit later, that produced a result and ultimately a series of figures. And again, versioned code, which is stored in GitHub, data, upstream data stored in Synapse, and downstream results stored there as well. And ultimately, we're trying to do this to promote an ecosystem where research is conducted for others to consume and not just for the individuals carrying out the research. We're in the process of putting together a Nature Scientific data descriptor paper for the full set of the mPower data. It's our hope that, I don't know if it will be by the end of this year, but certainly by early next year, we would be releasing the full set of the mPower data more broadly to the research community. So that's a lot of background. Now I'm going to dive into the specific study that we're going to be looking at tonight, provide background about how it was designed, the types of tasks that participants were asked to complete, and then we're going to take a look at some of the data as well. So mPower is an app to help decipher Parkinson's disease. Parkinson's disease symptoms are very variable. Usually Parkinson's patients are only seen once or twice a year by their physicians, but it's well known that their symptoms are very variable in the interim. So you see these participants on wild roller coasters as far as their symptoms are concerned, and the dosing of their medication, for instance, is really only being seen in these snapshots of time. And so putting an app in their hands that have some sort of surrogacy towards what their symptoms are like, we felt like would be very powerful. Ultimately, where we'd like to go with this at the tail end is to be able to distill a lot of that information down in a digestible format such that the participant could take that into their physician on those 6-month checkups and be able to say, hey, look, this is how my symptoms have been varying over time. So there have been almost 60,000 downloads of this app from the App Store. And I will be the first to admit that a large portion of that was due to the Apple bump. So when Apple announced this at their spring event right before they were announcing the watch, there were a lot of people that just downloaded it, wanted to take a quick look at it, and never touched it again. But we did have over 16,000 participants who consented, 15,000 who went through the full enrollment process. 78% of these participants actually chose to share their data more broadly for this particular study. And 17 of those patients, 1,500 actually had Parkinson's disease. So this app was opened up to any individual who wanted to participate, such that there would be a control population as well as self-reported Parkinson's patients. Now, the types of data we can collect with these apps, I think this is really important. There are very standard measures that are often used to assess a lot of these symptoms. For instance, surveys. Surveys are very high friction. They tend to be long. They're infrequent. On the bright side, a lot of these mechanisms have been validated in larger cohorts, and they're the basis for most publications. But we can start to take a look at other ways of measuring some of this information, such as structured activities, which I'll touch on in the next slide here, which can be done much more frequently and have minimal, mild friction. Unfortunately, they have minimal validation at this point. That's part of why we're conducting this study, though. And there are also passive measures, and this is something that the early versions of mPower really haven't harnessed fully, but we're hoping to add them in the future. But essentially having passive measures that the phone is recording with participants' consent, obviously, that might be indications or predictors of how well or how poorly they're doing. So there are generally, people believe there's sort of 4 major symptoms of Parkinson's disease: motor initiation, gait and balance, hypophonia, and memory. And so there are a couple of well-validated surveys which we ask participants in the app. We ask them to do it at baseline and once every month. But we also had structured activities that they could do. We have a tapping activity where they're asked to tap back and forth on the screen as quickly as they can for 30 seconds. We have the actual coordinates of where they're hitting on the phone, so you can see how accurate they are with actually tapping in certain locations. We also have the total number of taps that they're able to do. Parkinson's patients are asked to do this before and after medication, so you can start to try and tease out if any of these features are associated with how they're doing on their medication. There is a voice activity where they're asked to say "ah" into the phone for 10 seconds. There's sort of a cute little memory game where they're asked to repeat patterns that are lit up on the screen. And then there is a standing and walking activity, which is the data that we're going to be taking a look at later tonight. And this is a screenshot of each one of those tests. I actually have a screencast of this next one, which I'm going to do now. Gustavo, do you want to actually do the task? Do you want to do the walking test?
Myself?
Yeah, come up here. Yeah. So this is actually my phone. You're going to have to go down there because you're going to have to walk 20 steps. You can listen to Siri give you instructions. So you're asked to authenticate when you come into the app. This is the dashboard that you see, the types of activities that are there. So gait and balance. It says, please do not continue if you do not feel safe, but find a place where you can safely walk unassisted for 20 steps in a straight line. Put the phone in your pocket, and Siri?
Walk up to 20 steps in a straight line.
That's not straight. So this is actually very important, and we're going to hit on this in just a second. So a lot of people who are doing this test see exactly what Gustavo just saw there. They start walking, they get about 8, 9, 10 steps in, and ultimately they have to change course or they have to stop and turn around
and stand still for 30 seconds.
So the next thing they're supposed to do is turn around and stand still for 30 seconds. I could only even wait 5 seconds for the screencast because I'm not that patient. But ultimately what we're going to be looking at for this for the hackathon tonight is just the outbound walking test. So those first 20 steps. So the hackathon, this is really what everybody is here for. Why are we doing it? We're trying to lay the groundwork for possible future dream challenges. We're trying to give people a sneak peek into what I mentioned is soon to be a fully released set of mobile data from this app, and also hopefully to help improve the future iterations of this study. So the types of data that we're going to be giving out, we have device motion readings for over 3,000 walking activities. So this is, well, I'll touch on what that is in a coming slide. We also have metadata about these activities, essentially what type of phone it came from, version of the app, the timestamp of when it was actually done, so you could see if somebody's doing this in the middle of the night versus the middle of the day, maybe that makes a difference. We also have iPhone's estimate of the number of steps that were done. So we have some sort of grounding. We don't know if it's necessarily the truth, but we have some sort of grounding of what Apple has estimated the number of steps in this sequence was. And then for 1,000 of these 3,100 or so walking activities, we have the self-identified professional diagnosis of Parkinson's disease. So we actually have 500 cases and 500 controls, which we have made available. And this is all being made available through Synapse. There's all sorts of documentation on the Hackathon site, which I'll point you to afterwards. But just quickly, the types of device motion readings that we're gathering, we have user acceleration. So the user acceleration is the measurement from the accelerometer minus gravity. And all of these measurements are done in the reference frame of the phone. So X this way, Y this way, and Z right through the middle of the phone. So There is a gravity measurement that breaks this down in XYZ coordinates. There's user acceleration, which breaks it down into XYZ coordinates. And the sum of those two is essentially the full accelerometer readout. We also have rotation rate and attitude, which can actually help to sort of take this reference frame, which is the phone, and put it into a global reference frame, which would be the individual or three-dimensional space. And your mission, should you decide to continue on with the hackathon, we have three sort of suggestions of directions that you guys can take this. If you have other ideas, awesome. I think that's great. But the three topics that we think are interesting with this data, the first is unique patterns of activity. So participants were asked to walk regularly for 20 steps, but as we saw with Gustavo, even in a controlled environment, it's not necessarily the case. This is another example of what participants might be doing, thanks to Monty Python. Thanks to Chris Bear for pointing this out to me. And interestingly, when you start to dig into these data, you don't know if the person is actually doing that, but you see some really, really interesting patterns. And part of what has been fun, I know, for Elias and myself as we start to dig into this data is you can start to try and figure out what the person was actually doing. You can start to see, oh, the person must have walked out a ways, looked at their phone, put it back in their pocket, and then kept going. Like, those are the sorts of patterns that you can actually see as you start to play with these data. So, can you determine clusters of strange behavior, whether that be purposeful or not? Like, do we see people that have to change course like Gustavo did in his test? So, is there a cluster of outliers that, maybe if they were given better instructions, would be able to provide interesting data? Or maybe there's a cluster of people who are sprinting or who are doing jumping jacks. We don't know. But can you determine interesting clusters of strange behavior? So heel strike and their regularity, which is necessary for second order features such as the frequency of their steps and the magnitude, is very, very important. This is actually a clinically validated measure, which is essentially the inner step frequency. So essentially the variation that you're seeing, are these people able to walk at a regular rate, or is it very variable between each step? And Elias will show some examples of the actual data. It's essentially a peak detection problem. And then lastly, classification of Parkinson's based on gait. We're going to be releasing 500 Parkinson's cases and 500 controls. What are the things that allow you to classify those individuals into their respective categories? Are they simple primary features? Are they secondary features that you have to extract, you have to extrapolate away? It's for you to figure out. So I'm going to hand it over to Elias here to give some examples of the gait data. Here we go. Yeah.
All right. Okay, thanks, Brian. So now we are going to see some very interesting patterns. Let's start with here, the acceleration patterns. Okay, so this is actually a case that's actually a participant that did very regular data. So we actually believe that this participant actually was able to follow the instructions, right? And as Brian was saying, right, here in the left column here, we have the total acceleration. That's the combination of the acceleration due to the movement of the participant plus the acceleration due to the gravity. Here is just the gravity component, right? And here is just the component due to actual movement of the participant, okay? Here, in the first row here is actually the x-axis, here y-axis, and here is the z-axis. And as Brian said, right, these axes, they are in relation to the reference frame of the phone, right? So here is the z-axis, right? It goes through the screen of the phone. Here is the positive values of z. Here are the negative values of z. here is the y-axis, positive y, negative y, and this is the positive x and negative x, okay? And we see, for example, that this participant here, what's interesting to see is that here in the y-axis here, for this participant, it's very close to 1. And by the way, the acceleration here is measured in g's, right? So this tells that actually this participant had the phone like this, upside down, right? It was probably in the pocket. We don't know if it was on this pocket, if it was on this pocket, but it was in the pocket probably. And as he walked, right, because of the movement, we see these tiltings here in all the 3 dimensions, right? And this is a very different pattern from what we see here for the second participant here. So now we see for this guy here, right, that most of the accelerations here is -1 on the z-axis. So looks, this participant was probably holding the phone. Here is a little bit of negative on the y, so there was a little bit of inclination. And he probably was, during the whole task, he was actually holding the phone, right, instead of putting in the pocket. And we also see that, it's much smoother, and also the scale is much different from the first participant, where you see these really big accelerations there, right? This is another one, right, that probably had the phone on the pocket, and upside down. Most of the gravity acceleration was here, right, close to 1, right? But what's interesting about this one is that this person actually did walk a little bit, stop it, and then start walking again. But as Brian mentioned, there is some really very interesting ones, right? So look at this one, for example, right? In the beginning, most of the acceleration is -1 here, right? So it was actually holding the phone was probably in the pocket like this. Then the person decided to take a peek. We see now that most of the acceleration here in -1 on the z-axis now. And then he put back on the phone, but now upside down, because it went from -1 to +1, right? So it's very interesting. This is another one that actually started probably holding the phone, right? And then decided to put it in the pocket, upside down. And as I said before, we see here, right, that the acceleration is much, much smoother here than after I actually went to the pocket, like this, right? And this one actually left the phone on the table, and then put the phone and just keep walking, right? And finally, this one just left the phone on the table. That's all he did. Right? See here the scale, so yeah. So as Brian said, the task for this, your task here is actually, can we actually determine, right, which participants actually follow the instructions from the ones that did not, right? So that's the first task. The second one has to do with heel strikes, and as Brian mentioned, this is actually a validated, clinically validated measure, right? And here I'm just showing a simple example. It really boils down to actually detecting peaks. Here I just look at the vertical acceleration because that's the one that is easier to determine, but all we really want is determine these peaks, right? And get some features out of it. And it's really important to have an idea about regularity. So for example, you can just take the variance of the interval, of the strike intervals, for example. And finally, we have the cases versus control classification. Right. And what I did here was very simple dry run, just make sure that there was some signal in the data. So I just extracted very, very simple features, like, for example, for each one of the 3 axes, I just look at a bunch of summary statistics for each of the axes and correlations, autocorrelations, right? Just throw a random forest. And we see here that actually the AUC is here close to 0.65, right? So there is some signal. Here is actually just a sanity check where I actually shuffle the labels, and the AUC here is just around 0.5. So that's the third one. So get some features and build a classifier out of it. Right, so back to Brian.
Thanks, Elias. now on to the hackathon. So the room next door is going to be the hackathon room. There is pizza and beer out in the hallway out here. I think that's only going to be available for the first hour or so. So go get some food, go get a beer. We have a whiteboard in the other room where you can write ideas up there to try and help recruit teammates. So if you are really interested in question 1 and have a technique that you're interested in applying there, put it up there. There are pieces of paper there where you can write your team name and put it on a table. There are a bunch of round tables, so go organize. Documentation is out again at synapse.org/Dream Hackathon. And I believe anybody who has already signed up for their pre-registered for that should be getting an email, should have already gotten an email or will get one shortly with credentials to log into an Amazon AMI with all of the sort of necessary Synapse client stuff installed such that you can hit the ground running and then hack away. And we have about half a dozen folks from Sage who will be available to answer questions in the other room too, but otherwise have at it. Yeah, absolutely. So we have Laura Mangravit here, Elias in the back. We've got the 3 amigos there, Taya Norman, Bruce Hoff, and Chris Baer in the middle. So question up front.
Will the Amazon instances be running continuously after like 9, or will it be running through tomorrow?
Yes, good question. So the Amazon instances will be running all the way through the hackathon continuously. If you are interested in, either working later after things get done tonight, or if you have models that you're going to start running tonight, overnight, they'll be up and operational until after things conclude tomorrow. And actually, the one thing I did forget to say is at the end of the day tomorrow, at the end of the hackathon tomorrow, we're going to invite each one of the teams to give a 2-minute lightning talk about what they found. Very, very informal, but a way to communicate back to the group what they've been seeing. So, Stephen, was there something?
Just when you go out to get the pizza, it's actually right here, and to make it work kind of logistically nicely, stay to your pizza side and work your way around to the bar side. And there's soft drinks and water as well. So it's here, so it's
I always like to stay on the pizza side, and that's the right side to be on. So, all right, have at it.